Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and this is the conclusion of the lecture entitled Numerical Approximation of Definite Integrals. When we left off, you were working this problem, and I hope you didn't get distracted, but just in case you did, you have another opportunity to do it. So you know what to do. Let's see how you did. If you use the midpoint rule, you should have got this number. If you use the trapezoidal rule, you should have gotten this number. And if you used Simpson's rule, you should have gotten this number. If you didn't get these numbers, look at the way the calculation went and compare it against your formulas and find out where you went astray. Now for a better estimate, and what I've shown you here is what happens if you use a bigger n. So if you go 8, 16, 32, doubling each time, you can see that the error gets very small. Again, you can make it as small as you want by picking n large enough. We're also, as engineers, concerned with error analysis. So if you must use an approximation technique, it is important to know how accurate you can expect the approximation to be. So the following theorem, which is listed without proof, the proof is an advanced calculus kind of thing, gives formulas for estimating the errors involved in the use of Simpson's rule and the trapezoidal rule, and also I show you what it is for the midpoint rule. In general, when using an approximation, you think of the error as the difference between this and the approximation. It actually can give you then lower bounds and upper bounds on what the integral value really would be. These bounds will give the largest possible error in the estimate, but it should also be pointed out that the actual error may be significantly smaller than the bound. The bound is only so we can say we know the actual error will be less than the bound. And there are some if parts. So we have to have the second derivative of f of x has to be less than or equal to k for the trapezoidal rule, and for Simpson's rule we have to have the fourth derivative less than or equal to m. So these are bounded and these are derivatives. And this means that the fancier technology, you have to have more stringent application to it. Okay, so EM represents the bound for the midpoint rule, ET represents the bound for the trapezoidal rule, and ES represents the bound for the Simpson's rule. So the midpoint rule and the trapezoidal rule, you can see, have the same bounds. And it is k, which is k is the maximum value of this second derivative, times b minus a whole cubed, divided by 24n squared. So you see, as n gets bigger, this can shrink to 0. Actually, now that I look at it, the midpoint rule actually is a factor of 2 better. It is 24, not 12, excuse me. Simpson's rule, however, is even more powerful because what it has is 180. 180 is way bigger than 12, and n to the fourth is way bigger than n squared. So this is the sharpest estimate that you can get. This is the most lax, this is the next best, and this is the best that you can do across these three. Here's a kind of problem that I sometimes would ask. Determine a value of n such that the trapezoidal rule will approximate the value of the definite integral from 0 to 1 of the square root of 1 plus x squared dx with an error that is less than or equal to 0.01. So I'm telling you what the error has to be less than. You know what to do. Let's see how you did. Well, here is what f of x is, and we find the second derivative. This is the first derivative, and this is the second derivative. Now we're on the interval 0, 1, so x is less than 1. So the maximum value of this on this interval is obtained when, because it's a decreasing function, it is obtained when you're at 0. And so that means it's 1. So that's the maximum. So by the theorem we just talked about, the absolute value of the error of the trapezoid rule is less than or equal to, it is b minus a, which is going to be 1. I get 12n squared here, and this is 1 because of my analysis here. So this absolute value of the error is less than or equal to 1 over 12n squared. Now I want this to be less than 1 over 100. This is 1 over 100. So I say 1 over 12n squared is less than or equal to 1 over 100. I realize then that means 100 is less than or equal to 12n squared, and I can solve this, and n has to be bigger than or equal to 2.89, which means since n is an integer, it's going to be 3. So if we choose 3, then what happens is this is the approximation that you get using the trapezoidal rule, and it is this number. So by adding and subtracting this, the error from the estimate, we can know that this integral is in between this two numbers. Here's another problem for you to consider. This is a very applied problem. The widths of a bell crank are measured at 2-inch intervals as shown in this figure. Find the area of the bell crank if the two connector holes are each 2.5 inches in diameter. Very applied problem, and again, you want to use a calculator for this. You know what to do. Let's see how you did. Well, so you find using the trapezoidal rule, here's the formula. These are the numbers that you put in. This 2.0 divided by 2, that ends up being 1, but that's times this entire sum. Should have had parentheses there probably. So the area of the trapezoid is this. But then there are two circles that have to be subtracted off, and this is pi r squared. That's really the diameter over 2 squared, but it's the same kind of formula. And so the area of the circle, I said that the diameters were 2.5 inches each, so that's the area of the circles, and so the total area minus the area of the circles gives you this as the area of the bell crank. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.